Okay, in this video I'm doing a makeup lecture that was happening during finals week, or pre-finals week, for my MAE 4353 class, and we are looking at the chapter from our Shigley textbook on rolling contact bearings. So ball bearings, cylindrical bearings, tapered roller bearings, those kinds of things. And so let's take a look at the theory and techniques for selecting proper bearings. And so this picture is showing a schematic of a ball bearing, and we see what is called the outer ring or the outer race of a ball bearing. We see an inner ring or an inner race of the ball bearing. We see one ball here, another there, and a series of balls distributed around the ring. And to keep the balls evenly spaced and to keep them from running into each other or all grouping in one area, there is a separator. This might be metal, might be plastic. There are lots of different kinds of ball bearings, but they're all going to have this basic kind of thing in common. And then other terminology would be the width of the bearing, the outside diameter of the bearing, shoulders of the bearing, a corner radius, and a corner radius here that affects how they might fit into holes or fit into shafts, those kinds of things. With this basic general structure, of course, the bore of a bearing, which would need to fit typically a shaft. Okay. We would see different kinds of geometries, including a deep groove bearing, which is a very standard ball bearing. A ball bearing that has a large segment cut away in the outer and inner rings to allow the more balls to go into this bearing. Feeding the balls into the bearing is tricky, and it involves basically feeding them in from one side until you've gotten all that you can in there. Then you space them evenly and put the separator on. Angular contact bearings, notice the geometry here is a little bit different, so this will be a little bit better maybe at carrying thrust loads. Shielded bearings would have a shield here. Sealed bearings would have a much more robust shield on each side, or a seal on each side. Self-aligning bearings would have a third part that would allow the bearing to rotate a little bit to account for shaft misalignment, yet not put large stresses in the bearing because of this external aligning element. A double row of bearings, when you'd like to have two bearings available but there's no space for two, maybe you can fit one double wide bearing. A different kind of self-aligning bearing that has an interesting outer race. This would be a thrust bearing, okay, where this type of bearing is called a radial bearing. The forces act radially outward from this ring. In this case, the forces act axially from one ring through the ball to the next ring. Okay, and this would be a self-aligning thrust bearing. Okay, we also have bearings that do not use spherical balls. Instead, these bearings might use a cylindrical roller or a tapered cylinder or a conical roller that might have straight sides or might actually have curved sides. The advantage of roller bearings over ball bearings is that the theoretical point of area of contact between a sphere and a flat surface is a mathematical point. Now, we've studied Hertzian contact stresses and such, and we know that they'll deform so that there will be a finite area of contact between a ball and a flat plate after deformation, but mathematically it's a point. Okay? For a cylinder touching a flat surface, mathematically the region of contact is a straight line. And of course that still doesn't have any area, but a straight line is infinitely bigger than a point. And a straight line under Hertzian contact stresses will produce a larger area of contact, therefore heavier loads for the same stresses, those kinds of things. So a simple cylindrical bearing, let's see, this would be a tapered roller bearing. This one looks, let's see, I better read the words here. Yes, a tapered roller thrust bearing. No, a tapered roller bearing. A spherical roller for carrying, looks like both axial and radial loads. This needle bearing is taking the idea of a cylinder to its limit, except it has very small diameter. E is simply a tapered roller bearing, and F is a larger angle called a steep angle tapered roller bearing. Okay, when we select any kind of bearing to do a job, we would expect that bearing to be able to carry certain loads, certain kinds of loads, maybe straight and steady loads, impact loads, whatever, and we would like that bearing to last long enough, whatever long enough means. Okay, and so when we talk about bearing life, that's one of the key aspects we will require of a bearing. We can talk about its life in a few different ways. One would be number of revolutions of the bearing. And because the revolution of the outer ring does more damage than revolving the inner ring, we typically talk about number of revolutions of the inner ring as opposed to the outer ring. Okay, and a bearing, it has reached the end of its life when there is first noticeable evidence of fatigue in the bearing. Another way to denote bearing life is the number of hours, okay, at a given standard speed, and again, until the first noticeable evidence of fatigue. Okay, now, how are we going to define and measure life? Okay, again, revolutions or hours at a given speed can be made equivalent to each other, and we said failure occurs when fatigue begins to happen. So the American Bearing Manufacturers Association, ABMA, okay, has defined that the failure is the first evidence of fatigue, and fatigue is spalling or material falling out or pitting of material falling out of 0.01 inch squared, so that puts some quantity on the first evidence of fatigue. Now, how do companies who sell bearings specify the life of a bearing? Okay, and there is a term called the rating life of a bearing, again approved by ABMA, used by most manufacturers. Okay, and you've got to get this concept. If I say a bearing lasts 1,000,000 revolutions, have I said anything useful to define what that bearing can do? And the answer is no, because what I may mean, it can last 1,000,000 revolutions with a half-pound load on it. But if I instead try to use that bearing with a 10,000-pound load on it, it may only last a few revolutions or a few hours or something like that. So simply saying a bearing lasts a certain amount of time isn't a complete statement. I've got to tell something about how it's been loaded, those kinds of things. The other thing is, bearing life is not a fixed number. Bearing life is a statistical thing. Okay, and so just because this one bearing lasted under a given load a certain amount of time doesn't mean others made out of the same batch will last that exact same time. There's a statistical distribution. So one of the things we talk about for ball or roller bearings is number of revolutions or hours that 90% of a certain group of bearings will achieve, okay, before they start to exhibit failure. Okay, this 90% number and the life that's associated with the 90% reliability is also known as the minimum life, also known as the L10 life, also known as the B10 life. They're all synonyms for the same thing. This is called the rating life of the bearing, okay? And it's the 10th percentile location of a bearing group's revolutions to failure distribution. 90% will survive, 10% will fail. Another life that's really not used very much is called the median life, or the 50th percentile. Okay, might also be called the average life of the bearings. Okay, we're not going to use that for anything, but it does, in fact, exist as a name. So, if I have a bearing and something's going to cause it to fail early, what may cause it to fail early? If it's a ball bearing, I might increase the radial load. That'll make it, for a given number of revolutions at speed, it may, or for a given speed and this load, it may not last as long. Or for ball bearings, I might add some thrust load to the ball bearing. We'll talk about that in more detail a little bit later. So, let's take a look at the factors that affect life. Okay, so bearing load life at a given reliability, and so this plot is a load, is a plot of the load on the bearing versus the life of the bearing. So this axis load, this axis life, and we would expect as load gets high, life would be low. As load becomes lower, life becomes longer. And that's the truth. What's interesting is the data falls on a straight line, not on a linear plot, but on a log plot. The data for load versus life of a bearing falls on a straight line on a log plot. That can be written, okay, for this, the equation of this straight line would be the load times the life raised to a 1 over a power, where a can represents the slope of the line, is equal to a constant. And so we might wonder what that constant is. And after many tests, this slope of the line related variable a has a value of 3 if we're talking about ball bearings, or a value of 10 over 3 if we're talking about roller bearings, which is either cylindrical roller bearings or tapered roller bearings. Okay, and so we understand now that life varies with the amount of load we're going to put in the bearing through this type of a power equation. Okay, we're going to put that in just a minute. So a bearing manufacturer might choose a rated cycle value of 10 to the 6 revolutions. Okay, that's 1 million revolutions. That's what a lot of companies use. Timken, on the other hand, uses 90 million revolutions. Okay, but the manufacturer has to decide what their standard life is going to be. Okay, and then once they've decided what their standard life is going to be, they can take any bearing, and now that we know that its life is 1 million revolutions, what distinguishes one bearing from another? It's the load that that bearing can carry and still reach the life of 1 million revolutions. Small bearings would have to carry small loads to reach 1 million revolutions. Big tough bearings would have to are able to carry larger loads and still survive to 1 million revolutions. And so this idea of a load which leads us to a life is called a catalog load rating. When the life is specified as a 90% survival, 10% failure, then that load is called a C10, okay, or a 10th percentile, in which 10% won't make it. All right, so the way we're going to use this equation is for a particular bearing that lasts a particular life at a particular load. On the left-hand side of this FL to the 1 over A equation, that same bearing, if I change the load to F2, is going to have a new life. And the new load times the new life raised to the 1 over A power, this product is exactly the same as this product. And so what we're going to do is use on the left-hand side of an equation what the catalog tells us about a bearing. Okay, the catalog tells us that a particular bearing can carry a load called C10, and it will reach the L10 life of the catalog, whatever it is, and that product of C10 times L10 raised to the 1 over A power, and only the L is raised to the 1 over A power, is what the catalog tells us about the bearing. Okay, but you know what? I don't plan to operate the bearing at this catalog load. I'm probably going to operate it at some different load, and so I may ask the question, what's the life of my bearing going to be? Well, this left-hand side of the catalog gives us the constant. If FL to the 1 over A is truly constant, I can use the catalog's numbers to determine the constant, and then I can plug in my load and solve this equation for life. Or I can plug in the life that I desire and solve this equation for the load that I could apply. So this becomes, one of these would be an unknown, one of these would be chosen, but the left-hand side lets me compute the constant by using the catalog load and the catalog rated life. Okay, so we will put it all together. Again, the C10, L10 to 1 over A. The catalog numbers give me the constant, therefore FL to the 1 over A equals that constant. Now, we may choose to change this L10 life, which is life in revolutions, into life in hours by saying life in revolutions is life in hours times the speed in RPM, revolutions per minute, times 60 minutes per hour, to go from life in hours. That multiplying by these two would give us life in revolutions, but we can do the same thing on both sides of the equation. And of course the n, we might be running at different speeds, and we would expect different lives or different forces, so we can use the equation either in revolutions orientation or we can use it in hours orientation. Okay, and so one of the things that this equation might be used for is selecting a bearing. So let's think about this. I plan to use a bearing and apply a known load to it. I've done the statics on the shaft and I know what force I'm going to pass through that bearing. I know exactly how many hours I need this thing to run at a certain RPM. Okay, I know that information. That's my design goal for this bearing. So I know the load, I know the life, I know the constant over here. So in fact, what I have on this side is an entirely known thing, or the constant. So what will I treat as unknown over here? What I'll treat as unknown is the C10 value. So the question is, what bearing do I pick out of the catalog? Okay, and meaning what load, minimum load number right here, will I pick out of the catalog so that that bearing will meet these requirements? Well, the L10 life, or the life in hours, is typically a constant, the same number for every bearing in the catalog. This is what varies from one bearing to another. The C10 number is what changes in the catalog. The life is typically 1,000,000 revolutions, or a certain number of hours at a certain RPM. So I go to the catalog, flip through it, and I see a whole bunch of load numbers, and I say to myself, will it work? Well, what I'm going to do is solve this equation for the C10 value. That's happened right here. And so again, let's look at what I know. I know the load that I plan to put through my bearing. I know the life that I desire for my bearing. I know the catalog life right here. I know A. From all of that, I can calculate a load number, C10, that I take to the catalog. I scan the columns until I find a bearing that can carry this C10 or more, and I know that this bearing will meet my requirements or even do better than my requirements. So here's an example of that type. We're going to consider the company SKF, and they rate their bearings for 1,000,000 revolutions of L10 life. And so 60 times the life in hours times their revolution is 10 to the 6 revolutions. Okay, let's see. That product produces a familiar number. Okay, Timken uses 90,000,000 revolutions. If you desire a life of 5,000 hours at 1725 RPM, with a load of 400 pounds force and a reliability of 90%. Okay, this is everything I desire in a bearing. 5,000 hours, 1725 RPM, 400 pounds of radial load, and a reliability of 90%. Okay, what catalog number would I be looking for when I'm going for an SKF bearing? So let's take what I know and put it into this equation. I know that my desired force is 400 pounds. I know that my hours desired is 5,000. I know that my desired speed is 1725 RPM, and to convert from minutes to hours, I'll multiply by 60. And now, the catalog life is the life rating of the catalog times the speed at which they rate their bearings times 60. Now, I don't know the life rating in hours, and I don't know the speed rating in RPM of this particular catalog, but I do know that this product is 10 to the 6th. So I'm not going to bother putting in the 3 individual terms. I don't know them. I just know that this catalog has a life in revolutions of 10 to the 6th. Plugging in everything, doing the computation, comes up with a 3,200 pound bearing. Now, one interesting thing that has not been computed here, but what is 5,000 times 1725 times 60, and how does that compare to 1 million? I'm going to go grab my calculator application and bring it over here if I can. Looks like I can. And I'm going to say 5,000 times 1725 times 60 is 517 million. Let me make sure I did that right. 5,000 times 1725 times 60 equals 517 million revolutions. So I want my bearing to do 517 million revolutions, but the catalog rates bearings at 1 million revolutions. Since I want mine to last longer, I can't go to the catalog and pick a bearing that would carry 400 pounds. That bearing would only survive, a 400 pound bearing in the catalog only survives to 1 million revolution. I gotta pick a bearing that can carry 3,200 pounds for 1 million revolutions, in the hopes that I'll have a bearing that can carry 400 pounds for 500 million revolutions. You get the idea. I'm picking a very powerful bearing, okay, to be able to go a lot more revolutions than the standard. Okay, so we understand how load, or the force we're going to put through the bearing, interacts with life. That was a log-log plot. Okay, but then there's another idea of reliability as a function of life. We said we were going to rate these bearings such that 90% of the bearings survive that rating number and 10% don't. Okay, so taking a look at this graph, they're called constant reliability contours, and this is load here, and this is life. They say it's a dimensionless measure of life called X. We'll see that a little bit later, but it's basically life over a standard life kind of thing. And for a bearings rated at 90%, here is how life varies with load along that very same straight line with that same kind of slope. But if we'd rather talk about a bearing with a different reliability, and notice this load went down. Let's say I'd like to talk about a bearing with a 95% reliability. That means more bearings of the batch have to survive to the failure point where we see evidence of fatigue. And if that's the case, then I'm probably going to, I can run bearings at one load to get 90% survival. I've got to drop my load to produce a bearing set, or to have bearings last the same to the set failure, but 95% of them survive. As a matter of fact, what load would I put on a set of bearings to guarantee that 100% of them, not a single early failure? And the answer might even be I have to put zero load on it, because there might be just a bad one that was manufactured seriously defective. And so I'm not going to have a load for 100% reliability. Now, this is a statistical phenomena on how bearing life behaves, and maybe you've had statistics in engineering analysis or some other place, and you know about Gaussian type statistical distributions. Well, there are many other kinds of statistical distributions. The one that describes the relationship between bearing life and load and reliability is called the Weibull statistical reliability model for bearings, so the Weibull distribution. And this equation says that the reliability of a bearing set is related exponentially to a non-dimensionalized life kind of thing, and let's see, this quantity X is a measure of life as compared to the L10 life. And the L10 life, of course, is the life at which 10% fail, 90% survive. And so if I'd like a life longer than the L10 life, then my reliability would go down. If I can handle a life less than the L10 life, I could declare that my reliability has gone up. Okay, so that's what X is. It's a life ratio. This theta and X0 quantity are quantities that have to be determined somewhat experimentally. Okay, it says theta is the characteristic parameter corresponding to the 63rd percentile. Don't know why that is, but it just fits the Weibull model. And B is, which is the power, is a shape parameter in controlling skewness. Don't worry about that. We'll come to this equation in just, we'll use this equation in just a minute. But this thing basically says, as our life ratio goes higher, then the reliability expressed by that, as our life expectations go higher, then the reliability of a particular bearing set is going to be said to go lower. If we want higher reliability, we may have to accept shorter life to declare from the same bearing set. Now it's time to mix everything together: load, life, and reliability. And we're going to have our key equation for bearings, one of the most important equations for bearings. So going back, remember our earlier equation, force times life to the 1 over A equals a constant. Therefore, this would be our desired side. This would be the catalog side, or what the bearing really does. But we no longer call this life. This is a life ratio, where X again is the ratio of the actual life to the L10 life. And so the X10 value is L10 over L10, and that's a value of 1. And so what we're going to do is rearrange this equation. So we have force in the bearing. This X term is going to be brought to the other side. So the force in the bearing that we're going to be picking is our desired force, the force we plan to put into the bearing, times our life ratio divided by the bearing catalog life ratio raised to that 1 over A power. Okay, but now we're going to take our life ratio kind of thing and bring in the idea of reliability. And finally, it boils down to this. Let's see. It boils down to our life for the bearing is the design life of the bearing times a ratio of life ratios to the 1/4. But that life versus reliability is modeled with this Weibull function. I can solve this thing, take this equation and solve it for that life. This is what the equation looks like. So finally, here is a design equation. This is the most important. So this is the big equation of this chapter so far. If I want to pick a bearing, I've got to decide 3 things that I want out of that bearing. What force do I need to put through the bearing? How long do I want it to last? And what reliability do I need for this bearing? We'll talk about why we might need certain reliabilities later. But once I've chosen the force I intend to put through the bearing, the life that I need it to last, and the percentage of failures that I can accept during that life. And the standard catalog life is 90%. But what if I'm trying to get to Mars on a machine and I just need superb reliability? I may need every bearing to have a 99% reliability, or maybe even a 99.9% reliability, because 90% would be totally acceptable. If I know the if I know the load I want, and I know the life, and I know my reliability, plug them in and solve for the catalog number, and I go to the catalog and I grab a bearing that can meet or just barely exceed this number, and I will have a bearing that will get the job done. Okay, now I point out some silliness of the author, that calculating that natural log is really difficult. That's a natural log of 1 over the reliability. But the natural log of 1 over the reliability can be expressed as 1 minus the reliability is approximately right. So we can rewrite our key design equation is that the catalog life I will choose when I'm ready to pick a bearing out of the catalog can be calculated as the force I intend to apply, the life ratio that I need, which is my life divided by the standard catalog life, divided by this denominator, which includes this reliability term. Okay, and this equation is useful when I want reliability greater than 90%. It does not work should I want reliabilities less than 90%, but I really should not be wanting reliabilities that are less than 90%. So let's look at an example of how this equation, and this is the key right here, we'll use it for lots of things related to ball bearings. It says the design load on a ball bearing is 413 pounds. Okay, and an application factor of 1.2 is appropriate. Let's talk about application factors. Application factors say, I know the load I sort of expect, but because there's some uncertainty in what this bearing will encounter, I'm going to take this load and boost it by that number just to account for stuff that I don't understand. And 1.2 is not a bad number. That says I kind of really do sort of know what loads this bearing is going to see. There's not too much that are expected. I think we're going to see some tables later on that might give suggestions on other application factors for things like, a nice running machine, 1.2 is nice. If we're dealing with a jackhammer type device in some way, lots of pounding, that 1.2 is probably not an appropriate number. We probably want to boost that to account for all kind of uncertainties in the load. This is sort of like a load factor, not a factor of safety really, but it's maybe related, but it's a load factor that amplifies the load. So I plan to apply 413 pounds, but I'm ready to deal with applying 1.2 times 413 pounds. And I want to do that with the shaft rotating at 300 RPM. And my life, I would like to be 30,000 hours at 300 RPM. Okay, and I'd like to do that with a 99% reliability. And that's what makes us use the larger equation. Without the 99% reliability, we actually could have gone back to the simpler equation that we saw earlier. We could go back to this equation right here. But we are asking for a very reliable bearing. Okay, so the question is, the catalog does not rate any bearing at 30,000 hours and 300 RPM. Okay, and it doesn't let me choose the load. I've got to go pick a bearing that has a load rating for it. So let's go work this equation. But we know that FD is 413 times the 1.2. XD we're going to have to calculate, and RD is 0.99. Now let's deal with this X thing. The X thing is the life we want divided by the standard life in the catalog. And this can be in hours, days, years, revolutions, whatever. It just needs to be on the same basis. So what I know about my bearing is I wanted 30,000 hours at 300 RPM. And when I take that number and multiply by 60, that gives me total numbers of revolutions desired. The denominator is the rated life of all bearings in the catalog, and that rated life is 1 million revolutions as compared to this product. What is this number up top? This number up top is 540 million. Okay, so I want my bearing to last 540 million times, 540 times the standard life in the catalog. So knowing my X value, which goes here, knowing my F value, which goes here, and knowing my reliability value, which goes here, I plug everything in. 1.2 times the 413. 540 is my life ratio. Okay, we are told that x0 in this equation is 0.02, and we are told that theta minus x0 is 4.439 right there, and we're told that b is 1.483 for the manufacturer that has given us tables in our textbook. And so we're going to take those numbers and use them. If we change bearing companies, we're going to need new numbers for these, although these are reasonable for most bearings. So this gives us all the numbers in the denominator. It gives us the power right here. And of course, this number is the 1/3 that we encountered earlier. And so calculate out all the numbers that are known on the right-hand side, and C10 is now known. C10 is almost 7,000 pounds. I'm only asking my bearing to carry 400 pounds. But if I went to the catalog and grabbed a 400-pound bearing and applied 400 pounds to it, how long would it last? The answer is 1,000,000 revolutions, and only 90% of my bearings would get there. If I want to apply the 400 pounds to the bearings and have it last 540 million revolutions, 540 times as long as the catalog, then I better pick a heftier bearing than a 400-pound bearing. And if I want those bearings, 99% of them, to survive under that load and life, then I better pick an even heftier bearing. So I'm going to go into the catalog and choose a nearly 7,000-pound bearing, a bearing that can carry 96 pounds. But if I apply this kind of weight or force to that bearing, it'll only last 1,000,000 revolutions with 90% reliability. But if I only apply 400 pounds to this bearing, then it's going to last my 540 million revolutions, and 99% of those bearings will survive. Only 1% will not make it to failure, or not survive to my expected life. Okay. Here is this is what I labeled subtle point, and this is important. A shaft generally has 2 bearings. Okay. If either bearing fails during the life of the machine, then it doesn't matter if the other bearing survives. That shaft is out of commission if either one of the bearings fails. So we need to talk about the system reliability of a set of bearings working on the same job together, such that they all survive and reach the reliability that you want. And so if I have a bearing A and a bearing B on the shaft, each having a reliability on its own, what's the total reliability of the system that those 2 bearings are in? And it's the reliability of A multiplied by the reliability of B. If I have 2 bearings on a shaft, each one of those bearings has a 90% reliability, then my system reliability for the shaft as a whole is the 90% times the 90%, or 0.9 times 0.9, which would be a 0.81, or 80% reliability. Each bearing is 90% reliable, but my shaft bearing system is only 81% reliable. So to account for that, if I want to reach a certain system reliability, then I've got to choose bearings with higher reliabilities so that their product gives me the reliability that I want. If there are 2 bearings, I want the product of the 2 bearing numbers to give me the reliability that I want. Or I would want the square root of, if I want 90% reliability, I would want each bearing to have a reliability which is the square root of 90%, because the square root of 90% multiplied by the square root of 90% gives me 90%, or what I really mean is the square root of 0.9 times the square root of 0.9 gives me 0.9. But what is the square root of 0.9? Is that a number less than 0.9 or greater than 0.9? Well, since 0.9 is less than 1, the square root of 0.9 is a number which is bigger than 0.9. Let's just prove that. If I can find the square root function, 0.9. Where is that square root function? I don't use this thing very often. There's a cubed root. Is that a square root? It is. So almost 95%. So that number squared gives us 0.9. Let's go back to it. So I would have to have two 95% reliable bearings working together to have a shaft system that is 90% reliability. If I have a shaft with 3 bearings on it, then the cube root of my system reliability is what I need in each bearing. Excuse me. So that's what that talks about right here. Now, this one equation all by itself will let us do an awful lot of shafts where the bearings carry nothing but radial loads. The loads are perpendicular to the shaft, and they're fine if nothing is trying to move that shaft sideways. If something is trying to move that shaft sideways, that is called the thrust or the axial loading on the shaft, and something must resist that axial loading, and that axial loading can cause damage to the bearings, and we need to account for that when we select the bearings. So we get to a topic called combined radial and thrust loading, or another word for thrust loading is axial loading along the axis of the bearings and along the axis of the shaft. I'm going to stop this video and just to give it a nice breaking point, and then I'm going to start the next video right here at section 11-6.